Okay, another DEA video. This video will focus on some DEA code in R. All the code that we'll be using focuses on this benchmarking library in R. So some of the code that I showed you in a previous video, a simple one input, one output model. And if you have a one input, one output model, it's pretty nice to create a plot of input versus output, and we get our efficiency frontier plotted on there, and anything below the efficiency frontier is inefficient. Anything on the efficiency frontier has 100% efficiency. Okay, and to actually solve the DEA problem, we use the DEA command. X is our inputs, Y are our outputs. We'll talk a little bit about returns to scale in a little bit, but for constant returns to scale, put CRS. And if you wanted to compute dual variables, put dual equals true. I didn't do it for the one input, one output because they don't have too much meaning when you just have one input, one output. But then we can get the store the results or the outcome of that DE command into DEA results. And then we can access the efficiencies with $EFF. And here are those efficiencies. We can access the lambdas, which are the weights of the other DMUs in making up that DMU's target. And so here are the weights of the other DMUs for the target for A. And then, so each row corresponds to a different target for a different DMU. The columns refer to the DMUs that are making up the target. So because C had 100% efficiency and none of the other DMUs had 100% efficiency, only lambda C is non-zero. Lambda A, B, and D are zero because A, B, and D were not 100% efficient. And then the other thing that I put in here is I've taken those lambdas and multiplied by the input and taken those lambdas and multiplied by the output. And that's essentially computing the target X and the target Y for each of them. And we'll notice that in a one input, one output, the actual output matches the target output, but the target input is less than the actual input for all but DMU C, which was 100% efficient. So its target matches its actual input. So that's a one input, one output. Frankly, for a one input, one output, DEA is a little bit overkill, but it's helpful to kind of grasp the big ideas behind DEA. Let's upgrade to a one input, two output model. And so here I'm providing a list. There's still 4 DMUs. And so here's the first output. And then the next 4 values are the second output. And I need to tell it to create 2 columns here. And then I'll sort of name those columns Y1 and Y2. So if I run this, maybe it's worthwhile looking at what those inputs, still 1 column there, but the outputs now have 2 columns. Okay. So that sets up the data. For a plot, because now we have 2 outputs and 1 input, we can't just have input versus output. But the DA plot has dea.plot.transform. When you have multiple outputs, this is what you can use. I think it's dea.plot.isoquant when you have multiple inputs but 1 output. And here, what I'm going to do is I'm going to plot each of the outputs divided by the input. So this is output per unit input on both of the axes. And if I run that, I get a plot that looks like this. And let me move this out of the way so that we can look at this. And now we're looking at outputs on both of these, and we want to sort of maximize our output while minimizing the input. And so essentially we want to maximize the ratio of output over input for both of these. And now this black line represents the efficiency frontier in this sort of 2-dimensional output space. We can see that now C and D are 100% efficient, but A and B are not efficient. Okay, so now by going to multiple outputs, we get more DMUs that end up being efficient. And running the code to actually run the DEA, here's what we get. So efficiencies, A is about 93% efficient, B is about 66% efficient, C and D are both 100% efficient. And so kind of looking back at this picture, C and D are both on the efficiency frontier. A is pretty close to the efficiency frontier. B is quite a ways away from that efficiency frontier. Okay. Here's the targets. Notice now that the targets for A is a combination of both C and D, and about an equal combination of both. So if you take 11% of C and 12% of D and add those two together, you make a target for A. If you take 9% of C and 21% of D, that makes a good target for B. And then notice both C and D are their own targets because, so the C lambdas are 0, 0, 1, 0, which means that it would just pick out its own input and own outputs as its own target. Okay. I'll talk about these U's and V's. Those are the dual variables, essentially the values that they put on those inputs and outputs. When there's only one of them, not so meaningful, but when there's two, so when we have two outputs here, we can see how each DMU rates the two outputs relative to each other. And so for DMU A, if we can compare these two weights here for the outputs, it's in some sense saying that output 1 is almost twice as important to it as output 2 is. So 0.006 versus 0.003. So DMU A puts more value on the first output than it does on the second. Similarly, DMU B also puts about twice as much importance on the first input than the second input. DMU-C puts all of its importance on the first input because it scores better in that output. And then DMU-D puts all of its importance on the second output because it performs best under that one. And so kind of looking back up on this, you can see that C has the best ratio of input or output 1 to input. So it's the farthest to the right. DMU-D has the best ratio of output 2 to input. It's sort of the highest up vertically. And so that's why they sort of rate those as each of its most important outputs. And then if we kind of look at our targets here, one thing I'll point out, let's see. Okay, never mind. So yeah, for outputs, the target and the actual match each other. Once you get to more and more inputs and outputs, this is not always the case that they perfectly match each other on both, but the outputs for the target should always be larger than the outputs of the actual DMU. And the inputs for the target should always be less. And so in this case, DMU can see A can see a slight reduction in its one input. DMU B can see a rather large reduction in its input. DMU C and D are 100% efficient, so there is no reduction in their input. Okay, so that's a one input, two output model. Let's look at a two input, two output model. So now there's 8 entries for each of those, and both of them are set up to have 2 columns for the input and 2 columns for the output. Okay, running the code looks pretty similar to before, and so I'll run this again. In this case, with these inputs, these outputs, I've just sort of been making up numbers. But C and D end up being the most efficient again. A and B are less than 100% efficient. And so their targets are made up of some portion of C and some portion of D. You can kind of see the relative importance that they place on each of the inputs. Interestingly, only D puts some value on both of the inputs. Otherwise, A sort of thinks the first input is more expensive because you're trying to minimize you want to minimize the amount of value in your inputs. And so my guess is that A is actually using more of the second input, which is why it chooses to put the second input's value down to 0. And here are the relative importance of the outputs. And so B puts some value on both of the outputs, but A says the first output's more important. C says the second output is more important. D says the first value output is the only important one. Okay. And then here we can see the actuals and the targets. I will point out in this case here, we do actually see that the target for A, so the actual for A is 75 and 140 for its two outputs. The target for A has some slack in it, okay? And so target Y1 is 75, which matches the actual Y1, but the target Y2 is 175, and that there was sort of no combination of the efficient DMUs that could kind of perfectly combine to give you 75 and 140. So yeah, this will happen whenever you have quite a few inputs and outputs and not that many DMUs. And so in this case, the number of DMUs matches our inputs and outputs, and so we don't have a very well-defined problem. Ideally, you've got a lot of DMUs that you can be comparing relative to the number of metrics that you're using. Ideally, you've got more DMUs than you have metrics. And so in this case, we've got exactly equal the number of DMUs and the number of metrics for inputs and outputs. Okay. But our target inputs are always going to be less than the actual inputs for our inefficient DMUs. For our efficient DMUs, C and D, the target equals the actual because it's using itself as the target. Okay. Now, if we want to plot them, now that we have these weights, we can actually use those weights to essentially plot not the input versus the output, but the value of the input versus the value of the output using that DMU's weights or kind of values, U1s, U2s, V1s, V2s. So here what I'm going to do is I'm going to choose a focus DMU. And then I'm going to ask to do the DEA plot. And if you give it X's and Y's with multiple inputs and multiple outputs, by default, it'll just add all the inputs together, assuming that they're comparable, and add all the outputs together, assuming that they're all have the same value. But that's usually not the case. And so we can also supply WX and WY, which is the relative weights on the inputs and relative weights on the output. And so we'll choose to use the UX and VY values from our whatever focus DMU we want to focus on. And so let's start off focusing on DMU D. And you'll see that using the weights from DMU D, which would be this bottom row here, so it puts some importance on both of the inputs. It puts all the importance on the first of the outputs and not the second of the outputs. And so what we're plotting here on the Y and the X is the value of each DMU's inputs and outputs using D's weights. Okay, and so you'll see that D in this case is on the efficiency frontier. Happens to be that C is also on the efficiency frontier, but A and B are below the efficiency frontier. We can switch up and look at DMU A and use DMU A's weights. And so even though in the dual formulation, we can think of A is choosing the best weights possible for itself. Under those best weights possible for itself, it still has less than 100% efficiency. And actually, sort of, you can look here and can see that A is using 1 unit of input, but producing less than 1 unit of output. We see that C, though, is using 3 units of input and producing 3 units of output, or 3 value units now, if we're measuring things in value. We can look at B. Notice that B uses a combination of both C and D, and so it views both C and D as efficient in its metrics. Okay, whereas A used only C as its target, and so only C was on the efficiency boundary. And so if we go back to A, according to A's weights, C is efficient, but D is not. Okay, which is fine because we're only really coming up with A's efficiency scores based off of A's weights. D's efficiency score depends on D's weights and not A's weights. Let's, for completeness, look at C. And we can see that C sees itself as 100% efficient and sees everybody else as less than 100% efficient. So that wraps up maybe some code in here. I'll have another bit of code that I'll show you in a later video. But this is a good example of how to use dea.plot as well as the dea function, both from this benchmarking library in R.